Thank you. I've got a few. Well, thanks for joining anyway. This is going to be a really exciting seminar, and I really appreciate you taking the time. I've got a few announcements to make up front, and then I'll get out of the way and make room for our exciting talks today. Um, as you all know, this is the annual seminar for the Venables Award for new developers of open source software for data analysis. Before we get started today, I'd like to start by acknowledging the traditional owners on the land in which we all meet today. This will be different for all of us, but for me, it's the Dharawal people. And I'd like to pay my respects to elders, past and present, and my respects to any Aboriginal and Torres Strait Islanders who are tuning in today. The goal, I guess, of this award is really great. It's to encourage new open source software development in the Australian community, and with a particular view to support efforts to develop and share data science and statistics methodology. This wouldn't be possible without the generous help of our sponsors. This award is sponsored by the ARDC, the Australian Research Data Commons, which is a federally funded digital research infrastructure facility. For those of you unfamiliar, the ARDC aims to accelerate Australian research and innovation by driving excellence in the creation, analysis, and retention of high quality data assets. And they partner with the research community and industry to build leading edge digital research infrastructure to provide Australian researchers with a competitive advantage through data. So the sponsorship of this award is in aid of recognising the valuable contribution made to research when new ideas, methods and models are captured as software outputs in this uniquely actionable form of knowledge representation. So I'd really like to pay our thanks to the ARDC for their support of this award. I'd also like to thank the judging panel this year for volunteering hours of their time. It was a difficult task, so difficult in fact we've jointly awarded the award this year, which is really exciting. I'd like to thank the Statistical Society of Australia for helping support and run this event, and in particular the section for statistical computing and visualization for organising and administering the award this year. So it's a very special award. It's the Venables Award. While I'm sure Bill won't want me speaking too much about himself, being as humble as he is, I do want us to just acknowledge that the namesake for the award, Bill Venables, pioneered the use of F and consequently R languages in Australia. I'm sure many of us are familiar with the book Modern Applied Statistics with S, co-authored with Brian Ripley, and it was the primary manner that many analysts learned their trade across the globe. And I'm sure for many people on this call, Bill's tutorials on data analysis with S and R were their first entry points into working with data. So Bill's contributions are numerous across ecology, environment, climate change, and more, as well as being a mentor and guide to countless students. So we sincerely thank Bill for his contributions, and we're honoured to have this award, and it's great to see it encouraging more development in this field. We've got a really good agenda today. We've got two talks, and we're pleased, as you're no doubt aware from our announcements, to jointly award the Venables Award this year. It's gone to Alex Lee for his software whereabouts, and to Rob Moss for his package on particle filters for Python. Alex and Rob both join us today, and they'll be giving a 20-minute talk showcasing their work, and there'll be some time for Q&A as well. Now, I haven't actually set up in advance who's going to go first out of Rob and Alex, so I'm going to seek one of them to volunteer. Who wants to get in first and go first with their talk? Rob, if you want to, that'd be fantastic.
Sure.
Excellent. Well, look, Rob, while you get your screens there organised, I'll provide a brief introduction for those of you who are not familiar. So Rob Moss is a Senior Research Fellow in the Infectious Disease Dynamics Unit at the Melbourne School of Population and Global Health. Furthermore, his research focuses on predicting and mitigating the burden of infectious disease epidemics through the use of computational models and Bayesian inference. This work has directly impacted infectious disease policy and practice in Australia and overseas, and he's a member of Australia's National Respiratory Infection Surveillance Committee and the WHO Influenza Modelling Group. So thanks very much, and take it away, Rob.
Thanks very much, Dean. I hope you can all hear me.
Yep.
I have a tendency to have audio issues, so please let me know if you don't, if I'm not coming through clearly. But
Yep, loud and clear, and we can see your slide. Thanks, Rob.
fantastic. Okay, so yeah, look, this was an absolute pleasure and a surprise to be a co-winner of this award. And as I was preparing this, I realized the package name isn't really great. I'm not really sure how to pronounce it, so nicely avoided even trying to pronounce it, Tim. So I'll talk a little bit about the method itself for people who aren't aware of it. But most of my work involves fitting dynamic models of infectious disease epidemics to surveillance data using a variety of Bayesian inference techniques, but quite often particle filters. So at a really high level, I think probably the most common use of Bayesian inference to combine models and data is where you have your model and you have a choice of prior distribution, you have some data, and you write down a likelihood function that relates the data to the model, all for the purpose of sampling from your posterior distribution. For me, it's usually for posterior predictive checks, trying to predict what other data generated by the system should look like. And the standard sort of methods for this are typically Markov chain Monte Carlo methods, whether it's Metropolis Hastings, Gibbs, particle MCMC, Hamiltonian, Monte Carlo. But a lot of my work has been on sort of real-time forecasting, getting data daily or weekly, but quite often daily, and generating new updated forecasts each day, where sometimes these MCMC methods just aren't efficient enough, or I don't have access to computers that can run them more quickly enough. And so particle filters are a way of avoiding having to refit to all the data when you get new data, where the problem becomes if you have posterior samples fit your data up to some time, say up to yesterday, and you get a new data point for today, and you want posterior samples for your model fitting to all that data, that you only have to take your posterior from yesterday and update it to account for this one new observation. So they're computationally a lot quicker because you're doing a lot less work when you get a new data point. They are less robust. There's no sort of perfect solution here. So there are trade-offs here, and sometimes these methods sort of fall down. But when you want to update an updated posterior quite quickly, they're at least worth trying. And broadly, there's a whole family of algorithms here, but the basic idea is that you have a, say, prior distribution, and you draw a finite number of samples from this distribution, helpfully called particles. And if you've ever tried Googling particle filters, you'll probably come up with a lot of engineering papers about actual physical devices to filter particles from air. So it's not the best name, but we have this finite number of samples from the prior. You simulate them forward in time until you have a data point, and the likelihood of getting that observation from each of your particles will vary. And so you reweight each particle. The particles for which have a higher likelihood of generating this observation become upweighted. The particles that have a lower probability of generating this observation become downweighted. And then you can resample from this estimated prior to get your posterior samples for your next data point. And you can just do this iteratively, step by step, for each data point in your time series. And there's so many variations of this very simple method that refine or introduce lots of different methodological tweaks and adjustments to each of these steps. But that's the basic idea: is you have your data, you fit your model to it, you get a new data point, you just sample from your existing fit, simulate them forward, and update it. So hopefully that's a very short introduction, but hopefully it sort of made sense to everyone here. And then what does it look like when you use these things in real time? Well, if you think back to 2020, and especially for those of us living in Melbourne with the lockdowns we were experiencing, we were getting data. At this point, I think we switched to generating forecasts each week, but we were getting daily counts of confirmed COVID-19 cases in Melbourne. Shown here is the black lines for two different times in 2020. We're fitting the model to that data, which is difficult because the data are incomplete and being updated, and the relationship between the true number of people infected in your population and the number of people that you've identified as actually being infected, it can be challenging, especially if you're relying on them to develop symptoms and seek healthcare. And then we predict the forward. And so we have these two forecasts generated a week apart. The vertical dashed lines just show the day on which we actually generated the forecasts. The data are available. There's a lag there because it takes a while for people to develop symptoms and then become identified as cases. We're doing all this contact tracing and looking at contacts of contacts. So there were cases who weren't identified for quite a while up until quite a while after they'd been exposed. The most recent data are highly incomplete, so there's a delay distribution that we try to estimate, and you can't trust the most recent data because of a combination of these consequences. But the upshot was that at each week we're getting new data. It was incomplete. We're learning about COVID-19 as it's spreading in our population, and we're trying to predict what those case counts will look like, up to 4 weeks ahead, which is showing here. And the yellow line is the true reported data after all the data collection had ended. And the forecast did a pretty good job of predicting the data and sort of trying to quantify the uncertainty and what the case counts might look like. And we continue to refine and develop these methods all the way through to the end of 2023 when we finally stopped doing weekly forecasts for government. But going through this whole process and having our models and data and using Bayesian inference week by week and providing these things that were actually affecting all of us, our ability to go outside or travel more than 5 kilometers or all those various things. That was quite scary. And I think the one thought that kept running through my head as we were continually updating our models and finding new ways to sort of extend these inference problems was, I've probably made a mistake somewhere, because I know when I write code, when I'm well rested and relaxed and don't have time pressures, that there are bugs in my code. So when we're working very, very long hours, day after day, in sort of high pressure situations, I've probably made a mistake somewhere. And I really hope that if I have, I can find it and fix it, and that these predictions that we're providing to government are, reasonable and plausible and not misleading because of a coding mistake on my part. So at one point I actually stopped in 2020 on the model development and on the sort of the science and the methods development, and went, all right, I need to improve my peace of mind. So this involves sort of redesigning the code, stepping back and seeing that all the different ways we'd sort of started using it that we hadn't previously anticipated, and going, how can we redesign it to better make these sort of things separate where they should be separate, and how can we test it? How can I write down lots of different, how can I express lots of ways that I expect the code to behave and then check that it's doing this? And I think, as we all know, you're your own worst editor. So when you do this, you can easily miss things that other people will find because you sort of read what you expect to see or what you meant to write. So we also had some peer review. My daughter was born during lockdowns, and this is her in 2021, finding my coding much more interesting than her picture book. But we did share the code and get other people to look at it to try and find mistakes. And so this sort of turned the code base into something that was more general than our specific problem, quite relatively flexible, but also really well tested. So I was confident that it was, if not correct, under all circumstances, quite reliable. Along the way, we have these issues around the data streams are always incomplete and being updated retrospectively. And so if your data for the last week have been updated, you've got to go back in that sort of sequential process of sampling from the prior to then calculated new posterior. You have to go back to the point where if you ran the forecast last week and you're going to run it this week, but data from 2 weeks ago have changed, you've got to go back 2 weeks and refit to all the modified data. And it can be surprisingly complex to define just how far back you need to go for some of these data streams. And it's always a real key goal I had was reproducibility in the absolute sense. So if I refit to the entire data series, or if I resume from a cache state like last week's results or the week before's results, and I have all these stochastic elements, not just in the model, but in the inference method as well, I should get identical results because I just do not want the possibility that the circumstances under which I run my model and the inference have any influence on the outputs and then the potential messages we're providing. And then boring but important, finding ways to reduce memory usage where you're trying to run forecasts, say for 8 different states and territories for say 2 or 3 different versions of the model, all on 1 or 2 virtual machines in the cloud. All these boring things, I think, if I do them once, then hopefully it makes it useful for other people to use because then they don't have to worry about it. And then this also then made me think, well, maybe I can devote some of my time to thinking, how do I make this easy to use? So even if it's sort of capable of being applied to inference problems other than my own, that doesn't necessarily mean it's easy for someone to pick up. So I was trying to spend a lot of time thinking about, well, what's sort of the least amount of what's the least sort of onus I can put on someone to define what the simulation model looks like, to make a workflow that keeps the various things like your choice of prior and your data streams all separate, because quite often when code grows organically from a small example, these things can naturally become tangled together. And just looking at ways to go, yeah, can I influence how people, by design, encourage people to use good practices and avoid sort of common mistakes that I've seen in myself, but other postdocs and students when they're sort of developing code for new sort of inference problems. And then I had this moment where I thought, well, I've got this great package. It's robust. It provides these useful inference methods. It's easy to use. So of course, yeah, they made a film about this. If you build it, they will come. I should just sit back and wait for users to start using it. And of course, that's not actually what happens. Even if you make the software available publicly, people don't magically discover it. And I am not good at marketing or self-promotion, but I think probably the biggest thing I did that I think has helped other people make use of the software is to really focus on the online documentation and say sort of, here's how you can use it for a reasonably generic problem. Showing by example rather than saying, oh, it's a good package for doing this stuff, actually showing, here's how you use it. The online documentation has a getting started guide that walks through constructing a model of a system, simulating from the model, generating data, fitting your model to the data, generating all kinds of summary statistics and evaluation metrics, producing and plotting forecasts, tweaking the inference method to improve the quality of the forecast. So there's lots of, it's divided into, I don't know, maybe 16 pages there. But each one's sort of a small, quite focused sort of step through this. And I think that's probably the single most useful thing I could do to help people use this package. And then, yeah, how do I feel it's useful, and I don't want people to waste time trying to re-implement some of these methods and probably make some of the same mistakes I've done and since fixed. I think you can just say, look, save your time, actually do the science or the interesting stuff, and please use my package to do the nuts and bolts of the inference. So you can rely on word of mouth. People saying, hey, I've used this. This is great. You should try it too. Come over here. Had a few users in the Department of Maths and Statistics here who have used it as a consequence of this. Mentioning the software package explicitly in papers where it's been used. So in the method section, if you say we used a particle filter method to fit the model to data, you name the package, that can help. Some people have found my package that way. I've written a Journal of Open Source Software article about the package, which is more about then having a measurable way of talking about who's using it in a way that sort of aligns with sort of research academic metrics, because people can cite the paper, and then I can talk about citations, because that's sort of the primary metric by which we evaluate impacts, it seems. And finally, giving talks either about research where I've used the method, or, and I think this is the first time, giving a talk explicitly just about the package, and hopefully saying to an audience who weren't aware of it before, here's something that might be useful to you if you have a problem that aligns well with this sort of method. And then so as I've had a few more users pick up the package and use it for their own, you find all these sort of unanticipated ways that people either use it or want to use it or try to use it. Everything from finding one or two small typos that either in the code or in the documentation that have then been misinterpreted, and you realize, oh, no, I thought that way, this was clear, but it wasn't quite clear. Finding ways to prevent users from making errors that I never would have imagined until I saw someone try it. And if you can't prevent them, at least try and warn them early, give them an error message before they start chewing up computation time. One user was trying to represent missing data in a time series using NaN values, which might sound reasonable, but as soon as you start looking at the past data and asking if it's been modified when you get, say, a new updated time series, NaN values aren't equal to other NaN values. Like, basically this meant, like, it sounded like a reasonable approach, but it just meant every time the inference method went, oh, the input data have changed, we've got to go and redo the entire estimation back from the first data point. One user had ordinal data and was following the Getting Started guide and was trying to calculate credible intervals, which just aren't really a sensible thing to do for ordinal data. So it was just, yeah, it's really interesting to see new ways that people would use it, and then to be, either update the package or help them out to make better use of it. So I think that's probably my time. I'd stop there, but I'd really like a big thank you to the Stats Society of Australia and ARDC for this award. To Bill Venables, to actually have you here and talk about this is in front of you is kind of amazing and a very pleasant surprise. And thank you everyone for listening. If you're interested at all, the documentation is online. There is a JOS paper, and on a related sort of topic around sort of computational research best practices, myself and some other people in our research networks have been building up some online training materials called This is My Lab Book around sort of version control and sort of related stuff on sort of computational research. But yeah, so thank you very much, and it's been an absolute pleasure. And if any of you do try to pick up and use this package at any point, email me if you about anything, any sort of problems, questions, or compliments. I'll take compliments. But yeah, thank you.
Well done, Rob. Thank you. Really good talk, and interesting to get a good mix of, the process as well as, the use case. And I think something we were blown away by this year with yourself and with Alex's submission was just the profound impact that it's had on society. That these tools, life-changing, hugely influential decisions that are being made off them. Which is great. I think that makes us all feel really good about the value that we can make and the importance of having these things to support us. If you have questions for Rob, we've got about 10 minutes of Q&A time, and I can see plenty of hands going up, and there's also some questions in the chat. So we'll or you can shout out if you want, if no one's talking. So let's have a look. I did see some hands up. Bill Venables, I can see your hand up, and it'd be great to hear from you if you had something to say. Go ahead.
Oh, thank you very much. Can you hear me?
Yes, we can.
Okay. Look, it was a great talk, Rob. First of all, I'd like to say I'm very, very pleased that this has gone beyond R, because I think there's a big world there beyond R, and I'm pleased that it's that the idea that this award wasn't confined to my home territory. And secondly, I'd like to say it's exactly the kind of talk that I was hoping would attract, exactly the same kind of package I was hoping would be attractive to the people running the award. So congratulations, and well done. And Well, the other thing I'd like to say is that I've always found that coding is not just a job you do after the idea. Coding is, for me, quite often a way of working out the details, the theoretical underpinnings of an algorithm or of a process or of a model. In other words, to really get to the gist of things, you really got to code it, and it's got to work. Now, the other thing about you're saying you're writing code and people always find errors in it or find things that you hadn't thought of. A piece of advice I'd give to everyone: you can't make anything foolproof because fools are terribly ingenious. So I'll leave it at that. Congratulations and all the best.
Thank you very much, Bill. And I must say, when I first was notified about the award, one of my immediate reactions was, oh, but it's not written in R. And I do use R as well. I use quite a lot of languages, but yeah, and you're right. No matter how robust you think it is, someone will pick it up and use it in a way you've never thought of. Thank you very much.
Excellent. Do we have anyone else that wanted to ask a question? G'day, Nick. Go ahead.
Hey, yeah, thanks. Yeah, Rob, thanks so much for a great talk. I was just wondering quickly, how did you engage with users? Was it like on GitHub, GitLab or something, or did they email you or?
Yeah, no, it's been quite old school. A lot of it has been face to face or through email. I've got
Face to face. Wow.
Yeah, no, I've
found you.
the people in maths and stats who found me was through a past PhD student of mine who had done some stuff on some of this inference, these methods, not as his primary focus, but he was aware of it, then telling colleagues down the corridor when he heard about what they were working on and said, oh, well, you don't need to implement that. Rob's already written it. And email. I had a master's student in the UK email me out of the blue because they'd been looking for a particle filter package, and they tried quite a few in R and Python, and none of them quite met their needs, and apparently mine did. Yeah.
That's
Yeah,
great.
so
Awesome.
nothing, even though the code's all up on GitHub and stuff, I don't think maybe one person is sort of interacted with me through that.
Yep.
Well,
Yeah, great. Awesome.
hopefully they're not turning up at your house at night with a laptop confused.
Yeah, I try not to provide personal contact details.
Fair enough. Hi, Di. Do you want to say something?
Sure. I'll okay.
No, okay, let's try that. Can you hear me okay?
Yeah, that's good.
Okay, great. My question actually is related to what Bill's last comment was. I'm interested to know whether you learned about the method after you coded it, or whether you changed the methods up from things that you were coding.
Well, Bill's definitely right in that you learn a lot by implementing it. There were definitely some of the algorithms that there have been one or two really nice textbooks that have delved into a lot of the different sort of extensions to sort of the core method. And one of them in particular sounded like conceptually quite simple and a really nice way of addressing this limitation where if all your particles are bad, they're all equally good as well. So if all your particles are terrible, if your samples just are in a really low likelihood area, the particle filter method just says, well, they're all okay, rather than they're all terrible. And reading through this textbook chapter that introduced, it's called post-regularization, but it's a relatively conceptually sort of simple statistical method to adjust when you resample your particles, to sort of sample from a kernel around them in some way. But it was only in implementing it that you became clear that some of the equations, like there were some details missing, or it was quite a long, complex technical chapter, but once you tried to write it into code, you realized, well, this only tells about 90% of the story, and there are definitely some decisions or assumptions that they haven't really mentioned that you have to make before you have a complete implementation. And I found several other papers by the same authors where they, I guess, elaborated on some of this in technical appendices. And And definitely there was another one that I read through and I haven't implemented yet. But again, thinking about how you would write it out, yeah, realizing this actually works a bit differently to how I feel they've explained it in the text. I haven't changed anything about the methods. It's been more just about understanding that the way that they've been some of them have been presented in papers and textbooks hasn't quite lined up with how it's possible to implement them. I don't know. I hope that's answered your question.
Yeah.
I'm not being too critical of these papers. I'm sure if you read some of my papers and then looked at the code, you'd find that there's some sort of mismatches there between description and implementation.
Thanks, Rob. We might move on to our next speaker now. If you had any other questions for Rob, feel free to put them in the chat, and Rob might be kind enough to chat back to you, or I'm sure you can reach out using the support link that were mentioned. Thanks very much, Rob, and again, congratulations on the award and a great piece of software.
Thank you.
Up next, we have our second talk for this session, which is from Alex Lee. So Alex Lee, for those of you who don't know, is a machine learning engineer at Beyond Blue and an honorary research fellow at the University of Melbourne. His research is focused on applying machine learning and statistical methodologies to large-scale linked data sets for cancer research. As part of the Data Connect team within the Primary Care Cancer Research Group, he's helped establish the first primary care linked data resource for cancer research in Australia. In his current role, he works with large sets of text data, developing and deploying machine learning models for information extraction and modelling. He has a background in maths and physics and 10 years experience working in data science roles across government, business and academia. I'll hand it over to you, Alex, and we look forward to your talk.
Great, thanks, Dean. I'll share my screen. Okay. Can everyone hear that? See that and also hear me, sorry.
Yep, you're coming through loud and clear, and yep, I can see your slides. Thanks.
Great. Yeah, well, thanks everyone for coming along today, and also thanks to the organisers for the opportunity to present this package. Like Rob, did not expect to be a recipient of the award, so it's really good opportunity to hopefully also build the profile of the tool itself. So like Rob, there's also a COVID connection with this package. So I was working in Victorian government at the start of the pandemic, and we were all ended up doing a lot of COVID-19 projects, as you'd expect. And one of the problems that the Victorian Department of Health was facing was they would collect all this contact tracing data in the form of addresses and locations mentioned in what was essentially a SQL data, what was put into a SQL database. And they wanted a tool that could match locations mentioned in this text, sometimes with all sorts of spelling variations and errors, to high-risk locations. And they could include things like nursing homes and public housing towers and critical infrastructure. So they had contact tracing data and they had a list of high-risk locations. They wanted to match them together, and they also wanted it done at very, very short notice, within 5 days. So that was kind of the impetus for what would become this project. And so this is essentially a geocoding or record linkage problem that as we approached it. So for those who don't know, everyone's used Google Maps. When you enter in an address in Google Maps, you get back a standardized address along with some coordinates. And so that's geocoding. You're essentially looking up an address in a reference data set. And so we can think of this as a record linkage problem. So you might have your input address with, say, different spelling variations, or maybe the suburb or postcode is incorrect. And you have ideally a high quality standardized address data set. So that would consist of, in Australia, we have the geocoded national address file. So it consists of all standardized addresses along with pairs of latitude and longitude coordinates. And you want to find what is the best match between your input and your list of reference addresses. So you've got also some notion of similarity between these different texts. So geocoding and record linkage are like kind of key elements in a lot of data science projects. In a lot of data science workflows, you first need to actually take your messy data and then standardize it and convert it into a form where you can do some analysis with it. So some examples include linking patient records from different data sources, for example, GP clinics and hospitals, in order to carry out epidemiological studies. It could relate more to analysing actual movements through different geographic regions, so using those latitude, longitude values. Another application more in business would be finding the optimal location for a particular business, or in linking different customer address data sets in order to improve customer experience. So one question which comes up, well, hasn't this been solved already? And I mean, it's in some ways it's a relatively simple problem to state, and there are a lot of options out there. So there's the Google Maps of Geocoding API, there's Geoscape, there's Bing, there's Mapbox, there's a few other open source tools. But with the commercial ones, at least, one of the limitations is that often you can't send sensitive data, for example, if you're working with healthcare data, to an external API for privacy reasons. So you want something which can work, where you can do geocoding and record linkage in your own environment. Another limitation might be latency. So there are many cases where you might want to geocode millions of addresses or some large number of addresses in a short period of time. And so ideally having something which you can scale up is preferable. And related to that is the expense. So some of these commercial options can become quite expensive once you've got a large data set. And so the other thing is, whether it's open source or whether it's commercial, sometimes it's not always easy or user-friendly to install some of these. So given that we have a lot of really good open source, publicly available address data in Australia, then why don't we build our own? So there are three factors that make this challenging. We want to ideally have accuracy. So we want something that matches accurately to the standardized list of addresses. So we want many true positives and few false positives. You got that right? Yeah. We want something that scales, so that ideally it can work as well for 10 records or 1 record as it does for 1 million records. And another constraint, which isn't really relevant so much here, is that sometimes you can't actually send the raw data itself to a database. You might have to encrypt it first. And so there can be those sorts of privacy constraints as well. And all of these three factors are in tension, so that if you, for example, want something with high accuracy, that can come at the expense of an algorithm which is much slower. So going back to the record linkage problem, one way we could approach it is, well, we've got really good publicly available, at least in Australia, postal address data. So we can take our input address and compare it using some string similarity function with each of the entries in our reference data set, and then just pick the one which has the highest similarity score. One of the problems with this is obviously scale. So we've got around 15 million postal addresses in the GNAF. And so this isn't really a solution which will, it might work for one address in 10 seconds or a minute, but it doesn't really scale up. So as with other sorts of search problems, another approach is to try and reduce this search space so that you're not making 15 million comparisons, you're only making a much smaller number. And in the record linkage literature, this is often referred to as blocking. So you split your reference data set up into blocks of addresses and only search in a block which have high probability of being a match. So they're kind of promising candidates for being a match to your input address. And so then you can dramatically reduce the number of searches that need to be, or the number of comparisons that need to be carried out. And so this is what a traditional geocoding pipeline might look like. We start with the original address. We identify the different components: numbers, street, name, suburb. We carry out some spelling correction, so it's in a standardized form. And then at this point, we could use, for example, the street name or maybe the suburb as that kind of blocking key, that because there are a much smaller number of addresses which are in a Hindley Street somewhere in Australia than there are in Australia itself. And so these last two steps are where we are linking to that reference data set. So we've got that spelling correction, and then we get the standardized address and the coordinates. There's another approach which was developed in a couple of papers a few years ago, some researchers, I think they're all at ANU, and this is called a signature-based approach to geocoding. And so this is what formed the basis for the algorithm that Whereabouts implements. So the key idea, and intuitively, when you're talking about a location with someone, often you don't need to give them all the information in order for them to be able to identify what you're talking about. There's a lot of redundant information when describing location, and this is true in particular for street addresses. So if we just look at, well, first we just do our usual step, removing non-alphanumeric characters and converting to uppercase. But if we just look at this pair of so-called tokens, so a token is a string which is separated by a white space, we can say, okay, how many times does 217.243 occur in addresses in Australia? So that I'll refer to as a phrase. And it turns out there are only 4. So 217.243 is a useful signature or blocking key because there are only 4 addresses which match that. And if we approach the linkage problem in that way, then we kind of get robustness to spelling errors for free, because it doesn't really matter how these other pieces of the string are spelt. We can find a match to 4 addresses using just this component here. So that redundancy is really important in their algorithm. And you might think, okay, that's kind of a contrived example, which, I mean, it is. It's unlikely you're going to have that combination of numbers in any address, but it turns out this is quite a common property of postal addresses in general. So in the top chart here, if you look at you split all your addresses into phrases, and you look at how frequently they occur across all of the Australian address data, then around 65% occur once. So there's only one phrase which is essentially unique. And then if we look at the addresses themselves, we can look at the phrases that make up that address, so the pairs of consecutive tokens, and we can say, well, what's the frequency of the kind of like the best phrase in that address, the phrase that occurs least frequently over all of GNAF. So around just over 20% of addresses will have one phrase which essentially doesn't occur in any other address. And so just like in this example here, matched to 4 other addresses, it works really well as a kind of signature that uniquely or almost uniquely identifies the addresses. And then if we go to, we can tolerate some higher frequency, then we get a higher proportion of addresses that are covered. So this kind of observation justifies the effectiveness of their algorithm. So what you can then do is you take your input address table. So say I've got 3 addresses. I remove non-alphanumeric characters and convert to uppercase, and then I can split them into phrases. So look at how many times does this phrase occur? Well, it occurs once, it's just corresponding to this address. How many times does Adelaide SA occur? Well, that should occur twice. And actually, I've spelled that incorrectly, so it occurs once in this case. And so we can generate an inverted index table, which maps each of these phrases to the corresponding addresses where that phrase occurs in, along with how frequently it occurs, how many addresses it matches to. And we can do the same thing with the reference data. So we only have to do this once for the reference data set. Once we've got our entire GNAF of 15 million addresses, we formulate this inverted index, and we can count how many times does street Adelaide occur, around 21,000 in the GNAF. And then the key step is really just essentially joining these two tables together. So, and we only consider those tokens which are below a certain threshold in frequency. So we would ignore these because they're not really useful for identifying addresses anyway. So we might threshold it to say 100. And then we do a join, and then we can figure out which addresses are promising candidates for each of the input addresses. And skipping over a few details, what you can then do is convert this to, well, you can implement it in 10 SQL queries. So the key steps are creating those inverted index tables, joining them, and then there's a few other little steps, but surprisingly, this algorithm can be implemented around 10 different SQL queries. So the next challenge is, how do we actually implement this kind of algorithm? And one of the requirements I wanted for this package, and I mean, when I was kind of working on a prototype at the Department of Health, it wasn't really in a very user-friendly format, again, for similar reasons that Rob was talking about in terms of being under lots of time pressure and not really being able to write code which is particularly elegant. So, but we wanted this package to be easy to install. So you can just go pip install whereabouts, your package downloads. You don't have to do any other work in setting up a database or constructing these tables yourself. Ideally, it's as user-friendly as possible. And one solution I found is DuckDB, which is a relatively recent tool, where you can write SQL code and where there's a Python API. So it's a relatively new data analysis tool. Obviously, I don't want to overselling it, but it is really effective. For people who haven't used it, I'd highly recommend just checking it out. There's both R and Python APIs, and allows you to query tens of millions of records in seconds. You can install it with very little fuss. Unlike Postgres, you don't have to set up a server instance, and you can write your queries in SQL. So, for example, you can download the GNAF core, the kind of simplified version in a single file of the Australian postal address data. And in a few lines of code, you can just create a table to store that data, or you can even query it directly from the file on your machine. And so then you can run your SQL queries directly from within Python. Most of the, what you'd expect from SQL, the API implements. And so I'll just give a brief demo of how these kind of signature-based geocoding algorithms work. Hopefully I can still share my screen. Okay, is that visible? Yep.
Yeah, we can see it. Yep.
So we load up the package, load up a pre-built address database. Here's some, I think this is from some health services, and just done some bit of wrangling to create the full addresses. You can extract those, and then we geocoded them, however many, 171. And so you can see, I mean, in this case, the addresses themselves are quite high quality already, so you tend to get high matches, but it turns out to be quite effective and scalable way of carrying out geocoding. One of the problems is if you use those blocking keys made from phrases, like complete phrases like this, then if you've got a spelling error in the phrase itself, then it won't be able to match. And so then that causes problems. So another part of developing the package was to extend it to use so-called subtoken, I call them subtoken phrases. So rather than taking entire words or entire tokens, split that up into say 3 consecutive characters and look at the different combinations, and then look at pairs of those subtokens. And this improves the sensitivity, the recall of the algorithm, but it also, there's that trade-off in the sense that it increases the storage size and therefore reduces the speed at which you can carry out this geocoding. Another feature that's implemented by the package is to kind of combine different variations on these algorithms so that you can start with your input addresses. You can essentially use the faster algorithms to geocode the higher quality addresses, and the ones that that fall below a certain threshold in similarity, you then pass those to another algorithm which is maybe slower but can handle more variations, and then you combine the results at the end, and currently working on extending that to other algorithms. Here are some results from a few different data sets. I think this is from realestate.com.au. So again, reasonably high quality data, but still some inaccuracies. Whereabouts is in the red, and you can see Google and Mapbox and Nominatum. And we can look at whether we want that accuracy at apartment, house, or street, suburb level. You can see Google's consistently a really good option, but this package still does quite well. And I think it was one of the things I found interesting working on this was a number of little sub problems that I encountered. One was how to make it actually user friendly, how to host the databases. Like you've got these files of several gigabytes, and Hugging Face turns out to be a good option, so you don't have to pay for egress costs. There's the perennial data cleaning issues that come up in data science, and the ongoing challenge, which Rob has also pointed out, is how do you actually promote the package and get users to work to adopt it or to play around with it. So if you want to install it, you can have a go yourself, or if you'd like to contribute to the project, then certainly contributions are welcome, or any bug fixes or issues or feature suggestions. Or you can try it out online on Hugging Face. There's an interactive demo. And I'd just like to thanks to a few people. So Rob Lecht, former colleague who introduced me to Postgres many, many years ago. Victorian Department of Health for providing the initial use case, the Python open source community, Geoscape, and all the different government agencies for their a huge amount of work in collecting, curating, and making available these address data sets. And finally, the ARDC and Statistical Society of Australia. So thanks for listening.
Thanks very much, Alex. Yeah, really good. I mean, the judging panel for this one were really impressed with a couple of things. It certainly worked as advertised on the tin with very minimal fuss, and it just worked, which was really good. It was lightning fast, and I really like the way it combines sort of cutting edge research, cutting edge technologies, and cutting edge kind of code spaces and interactive hosting environment all together, which is just, if you go back 5 years, a lot of these things just weren't available. So it really is a way that we're taking science and technology and getting it in the hands of users, where if this wasn't around, most users are forced down this path of commercial software, which, as you point out, is often not appropriate. And it has such wide applicability. I like your COVID example, but I've dealt with this problem many times. So yeah, it was really good, a really nice experience for a learner too. I tried your code space, I read your documentation, I ran it manually myself, and it all just worked straight away, which was a really nice experience. And I think that's something that for scientists trying to publish software, trying to get the usability aspect of it down pat, so users will trust and use some software and not be scared of it from their first experience. It's easier said than done. So well done.
Great. Yeah, thanks very much. Good to hear. It's useful.
We welcome, got a few minutes still for questions. I know someone's got their hand up. I have to hunt through to see who it is. Bill, I think it's yourself again.
Very nice work, Alex. Way beyond my comfort zone, but I'm very impressed with the way you've handled it, and congratulations. That's all I wanted to say, really.
Thanks very much.
I can see we have, did someone else have their hand up? You got a few compliments in the chat there as well, Alex, which is good. Petra says your approach seems to perform well in comparison to Google. Yeah, that was really impressive. I thought as well. Wondering whether you have approached them about your algorithm as a way to promote.
I'm sure they've got plenty of good people who are doing geospatial work there. Or yeah,
They might take you out, Alex. You might be a threat. Nick wants to know. Oh, sorry, go on.
I was just going to say, I think one of the challenges, and there's some papers in the literature about this, is what are some good validation benchmarks, some validation data sets for geocoding and record linkage. And I think that the ones I used were from publicly available data, but they don't really capture all the different nuances and variations that you can encounter. So,
sure.
Yeah.
Nick wants to know whether you've considered submitting this to the Journal of Open Source Software.
Yes, I did. I did. It got rejected, unfortunately, but I'm going to. I'm still working on extending it to incorporate other sorts of record linkage algorithms, and I might submit elsewhere. Yeah.
David Price says, great talks and works, Rob and Alex. Yeah. And Nick, hi Nick, you want to say something this one?
Yeah, I just wanted to say I'm pretty surprised that Joss rejected it. It's quite strange. Yeah, so like I'd be happy to help, you ask, I'd be happy to help support you to try and get like another submission in. Just to clarify, so this is an implementation of some existing algorithms, right? So have they published software with this, or are they just like, here's a thing?
I couldn't find any. So one of the papers, there's an archive version, but I haven't seen an actual published version of it. And so that's that paper, which they explicitly write out those 10 SQL queries. I couldn't actually find a published version of the paper, and I couldn't find a Python package or R package or anything else. Yeah. Yeah.
Okay. Yep. And I was also just wondering, so then also, I guess like two things. One is, have you, this works for any GeoCode database, right? This isn't just like Australia. You can use anything that sort of has the same format as GNAP.
Yeah. So that's the other, I've been working with, I played around with US data, I've done some cleaning. It's quite a lot of work. And there was someone in Poland, a data analyst, who was wanting to use it for some Polish address data, which is kind of an interesting other challenge when you've got different sorts of characters and accents as well.
Yeah, totally.
Yeah.
And I think,
does it really work for? Yeah, sorry, are you good, Dean?
Oh, no, I was just going to clarify. I think it's the intention is you provide your own lookup database, right? If you're a health organization or institution or a department, but you can leverage these publicly available address data sets if they're available.
So you can download, there are pre-built geocoding databases you could download from Hugging Face. So you don't necessarily have to build it from scratch, but if you've got your own bespoke data, then you can do that as well.
Gotcha. But just to be clear, the method, provided the data is in sort of right format, it'll work. So I was also wondering if you've been in touch with the authors of these other papers to let them know that you've implemented there. Yep.
Yeah. So got in touch with Peter Kristen, who's does a lot of research on record linkage algorithms, and mentioned, because I presented this package at PyCon in 2023, and just mentioned that you guys presenting it. Just wanted to check it was okay with him as well. I'm with
Excellent. I also think it's quite possible the ABS could be interested in this as well as another. I'm not sure who to really contact about that, but that's anyway. Those are my thoughts. But very impressed. But
we are up to time now, but I'm sure the authors would be happy for you to reach out on their GitHub pages with questions or discussions or via their contact link. So I'd like to just conclude by again congratulating Rob and Alex for their excellent submissions. That was so interesting and different to anything we've seen. Great to see some Python. It's all really cutting edge and such a brilliant user experience. So it really makes me feel good about the future of scientific software and open source software. So glad the award was of some encouragement. Congratulations and well done. And I hope everyone attending today has learned something and has got some inspiration from it. Feel free to spread the word, and we look forward to future announcements about what's coming next year.